Operational amplifier. The operational amplifier is a direct coupled high gain amplifier to which feedback is added to control its overall response characteristics. It is used to perform a wide variety of linear functions, and it is often referred to as the basic linear integrated circuit, or more accurately analog integrated circuit. Sometimes it is also used for non-linear operations. Operational amplifiers originally used to perform mathematical functions such as addition, integration, differentiation, etc. in analog computers are now put to a variety of other uses, that is, as comparator, pulse generator, square wave generator, Smith trigger, etc. The schematic diagram of basic operational amplifier is shown in this figure. And its equivalent circuit is shown in this figure. In basic operational amplifier, there are two input terminals. Terminal 1 is represented by minus sign and terminal 2 is represented by plus sign. Terminal 1 is known as inverting input, while terminal 2 is known as non-inverting input. Voltage V1 is applied at terminal 1, that is inverting input, while voltage V2 is applied at terminal 2, which is non-inverting input. Nearly all operational amplifiers have only one output terminal. A signal appearing at the negative terminal 1 is inverted at the output, and it is called as inverting terminal, while a signal appearing at the positive terminal 2 appears at the output without any change in sign, and it is called non-inverting terminal. In this figure, input voltage Vi is V2 minus V1, and voltage gain AV is equal to VO upon Vi. Input voltage Vi is the difference of voltages between terminal 1 and terminal 2. There is only one output terminal, and output is obtained across load resistance RL, and output voltage is equal to AV into VI, as AV is the voltage gain equal to VO upon VI. This is low frequency equivalent circuit. In first portion there are two terminals, terminal 1 and terminal 2. Terminal 1 is inverting terminal, while terminal 2 is non-inverting terminal. Voltage V1 is applied between terminal 1 and ground, and voltage V2 is applied between terminal 2 and ground. Input voltage Vi is equal to V1 minus V2. Ri is input resistance. In second portion, it is a voltage source of voltage AV Vi connected in series output resistance RO, and output voltage VO is obtained across load resistance RL. This is the equivalent circuit of basic operational amplifier. Ideal operational amplifier. Ideal operational amplifier has following characteristics. Number 1, its input resistance Ri is infinity, and its output resistance Ro is 0. Voltage gain AV is minus infinity, while bandwidth is equal to infinity. Perfect balance. Vi is 0 when V1 equal to V2. When the voltages applied at two input terminals 1 and 2 becomes equal, input voltage Vi becomes 0, as Vi is equal to V1 minus V2. Zero drift. Characteristics do not drift with temperature. By the change of temperature, its characteristics do not change. These are important properties of ideal operational amplifier. We have two type of basic operational amplifiers. First is basic inverting operational amplifier. Circuit diagram of basic inverting operational amplifier is shown in this figure. And its equivalent circuit is shown in this figure. In basic inverting operational amplifier, the positive non-inverting terminal 2 of the amplifier is grounded. Non-inverting terminal, positive non-inverting terminal 2 is kept as grounded, while input signal Vs is applied to the negative inverting terminal 1. we can see in this figure, non-inverting terminal positive terminal 2 is grounded, while signal Vs is applied at inverting terminal 1, negative inverting terminal 1 through resistance Z or impedance Z. The feedback applied through the impedance Z dash from the output to the input terminal, and it is negative feedback. Vs is the input signal that is applied at terminal 1, inverting terminal 1 through impedance Z, and feedback is applied from the output terminal to the inverting terminal 1 through impedance Z dash as shown in this figure. If operational amplifier is considered as ideal, it will have infinite voltage gain AV, but AV voltage gain is equal to VO upon VI, output voltage upon input voltage. Therefore, for finite value of VO, the output voltage gain AV can be infinite only if the input voltage VI is 0. The negative feedback from output to input through Z dash serves to keep the input voltage VI at 0. Thus, terminal 1 will be at the potential of terminal 2. As terminal 2 is grounded, terminal 1 is thus virtually grounded, and no current flows from input terminal 1 to input terminal 2. I dash is equal to 0. This situation is depicted in figure B, where the virtual ground is represented by the double-headed arrow. This is equivalent circuit, and double-headed arrow shows virtual ground at the input. That is, current I dash is 0 at this place between two input terminals. Since input resistance Ri is infinity, current I through Z also passes through Z dash as indicated in figure. Current I, which passes through impedance Z, this current also passes through impedance Z dash, as no current flows between input terminals 1 and 2. This is also shown in this equivalent circuit. I current is flowing through impedance Z, and I current is also flowing through impedance Z dash. I dash is 0. And the voltage gain with feedback AVF. Voltage gain with feedback AVF is equal to VO upon Vs, and it is equal to minus Iz dash upon Iz. I is cancelled out and it comes equal to minus Z dash upon Z. Second basic operational amplifier is non-inverting operational amplifier. Very often there is a need for an amplifier whose output is equal to and in phase with the input, and in addition Zi input impedance is infinity and Zo output impedance is 0, so that the source and the load are in effect isolated. An ammeter follower approximates these specifications. More ideal characteristics can be obtained by using an operational amplifier having an inverting terminal for the feedback voltage and a non-inverting terminal for signals as shown in figure. This is the basic circuit of non-inverting operational amplifier. Input signal Vs is applied at non-inverting positive terminal 2, and feedback is applied from the output terminal through resistance R dash to inverting terminal, negative inverting terminal 1. With Zi equal to infinity and AV equal to minus infinity, AV voltage gain equal to VO upon VI equal to VO upon V1 minus Vs equal to minus infinity. So for finite VO, V1 minus Vs must be equal to 0, or V1 must be equal to Vs. So there is a virtual short at input terminals. Here also there is no current flowing through either input terminals, no current flow through inverting or non-inverting terminals. I1 is equal to 0, current flowing through inverting terminal, and I2 is also 0, which is current flowing through non-inverting terminals. Closed loop gain, that is voltage gain with feedback AVF, is equal to VO upon Vs, and as Vs equal to V1, it is equal to VO upon V1, and VO upon V1 is equal to R plus R dash upon R. R is the resistance across which voltage is V1, and R dash is the resistance used for feedback. This closed loop gain AVF is always greater than unity. If R equal to infinity and or R dash equal to 0, then AVF equal to plus 1 and the amplifier acts as a voltage follower. If R equal to infinity and or R dash equal to 0, AVF is equal to plus 1, voltage gain with feedback becomes plus 1, output voltage obtained will be equal to input voltage and in same phase. And in this way this operational amplifier acts as voltage follower. In this analysis of non-inverting operational amplifier circuit, we have used the fact that no current flows into either input and the potentials of the two inputs are equal. I1 is 0, I2 is 0, Vi input voltage is 0 because potential at inverting and non-inverting terminals are same. Vs is equal to V1.